My name is Geoffrey Eastway. Second time in a week that I've been talking about matters astronomical. I was absolutely privileged to get to talk to Cork Astronomy Club last Monday night on the subject of astronomical references in poetry. And it's a bit unusual for a club that's really very technical. But you know, they laughed in all the right places, and I had a polite round of applause at the end. I don't know, as long as they pay the fee. But today, why did I come? How did I get here? You don't usually associate art with astronomy, but I do. You know, I'm a mechanical engineer. I'm not known for art, my artistic abilities, which are zero. Hello, John. Good morning. Thank you for coming. I know nothing about painting. I don't mind a nice Goya or a Vermeer particularly, but the life of a mechanical engineer has been more to do with metals and pressures and keeping complex power plant running and that sort of stuff. But I have had a lifelong interest in stars and astronomy and sciencey sort of stuff. And Belinda Walsh, who organises the Arts Festival, had asked if I would do something that might have a sort of arty twist. It just so happened that 6 months ago, my brother, who lives for promoting mathematics in London, phoned me up. He said, I've just done a deal. He said, it's very unusual, out of my usual sort of range. He said, I just had the idea. I think he'd taken his kids to see a Shakespeare play. He said, there was a surprising amount of reference to numbers. So I thought, I wonder if he can do some sort of mathematics promotion on the mathematics of the Shakespearean era. So he contacted, for heaven's sake, he didn't hold back. He contacted the Royal Shakespeare Society, the Royal Institution, the National Union of Teachers, etc., etc. Everybody seemed remarkably interested. The whole idea is to integrate mathematics into a broader curriculum. Maths is something for everyday life. And he phoned me up. He said, the maths of Shakespeare. Of course, that was driven by the great earth-changing, humanity-changing experience of the original beliefs of 1,500 years or more that the earth was the center of everything. But new kids on the block sort of cast their minds a bit wider and said, no, not so fast. You know, there are a few features of geocentricity, were that to be true, that we can't square with what we're actually observing. And that process of 1,000 years worth of human thought built into culture and sort of almost day-to-day norms of the intellectual classes. Most people didn't give a monkeys because they were too busy striving to, get a bit of grain for the kids, and catch the odd salmon in the river and that sort of stuff. But amongst those people, generally clerics, generally church-related. And I'm here talking about the Western world. I don't know anything about Chinese, Indian, and very little about Egyptian thinking, although it was slightly influential. They thought, this cannot be right. Hence the title of my talk. This cannot be right, that the world is the center of everything. So I got a couple of notes, and I'm just going to use those as a modest prop. So, just by way of amusement and in some cases a bit of enlightenment, we're leading up to the period of the so-called Enlightenment, but Enlightenment for yourselves and possibly for me as well. I brought some modest bits and pieces. We can faff around making our own little Galilean telescope. I brought a telescope and what I prefer to use, which is a pair of binoculars, and I'll show you just how I set that up and what it's possible to see. Somebody's provided me with that water very kindly. I have my little Lego man. One of the key features of this whole enterprise of changing thinking is measuring angles in the sky. How do you actually do it? It ain't quite as easy as you might think. My son gave me a Christmas present a couple of years ago, which I'm completely delighted with. It has nothing to do with this, but I thought people might be interested. It's a little Lego orrery of the sun, the earth, the moon, and the sun. Not quite to scale, you can obviously tell, but actually the rotation, the whole thing is moving around slowly, and the sun and the moon is moving around the earth. It is roughly in scale, so the earth goes round in 365 days, during which time the moon goes round about 12 or 13 times, and so on. Some devices, a pinhole camera that you'll remember from your childhood, which was critical to this range of thinking. Some tops. My particular specialty as a young engineer 30 or 40 years ago was rotating equipment, and that sort of spilled over into a fascination for tops. We'll put the telescope up, and some slides of illustration. By the way, I don't know why I'm saying this, but everybody, I'm just thinking back to Monday night, everybody has been steeped as a child in one of probably the best known poem in the English language, probably the best known, most widely known, most widely spoken. And everybody here will know it. And you're all scratching your head. What the hell's that? I'll give you the first word. Twinkle. Twinkle, twinkle, little star. And I'm going to read it just for the hell of it. This has nothing to do with what I'm talking about, but it amuses me. It was actually written in 1804 by a lady called Jane Taylor for a children's magazine, which was published in 1806. And this has nothing to do with this, but it's a nice little poem, and it went down well the other night. Not a lot of people know that there are 5 verses. Everybody knows the first verse. Twinkle, twinkle, little star, how I wonder what you are, up above the world so high, like a diamond in the sky. When the blazing sun is gone, when he nothing shines upon, then you show your little light, twinkle, twinkle, all the night. Then the traveller in the dark thanks you for your tiny spark. He could not see which way to go if you did not twinkle so. In the dark blue sky you keep, and often through my curtains peep, for you never shut your eye till the sun is in the sky. As your bright and tiny spark lights the traveller in the dark, though I know not what you are, twinkle, twinkle, little star. Sorry, that's a little bit of padding. I shouldn't be using that sort of thing. But moving on to back to geocentricity, the Earth being the center of the universe. Why was I asked just quickly to the arts festival? Well, arts, I looked up what are arts. Arts have 3 particular features. Arts are creative. They involve the use of boundless imagination, and they evoke an emotional response. And I think that can apply not just to paintings, not just to poetry, not just to the music of Bach, but to the thought process, the just amazing thought process that went against everything that everybody who thought they knew something about it believed at the time. And my interest in astronomy, I've had all my life. I went to school in Cheshire in the northwest of England, and every day we used to pass the great Jodrell Bank telescope, this massive structure. Some of you will have seen pictures of it, a huge steel dish collecting radio signals from space. And that sort of sparked my interest, I suppose. I remember Dad taking me out into the back garden one dark night, and telling me that Yuri Gagarin was in that one. It was probably a plane. And in my recent researches, I looked up Yuri Gagarin, and his flight, actually, he was the first astronaut. He flew for an hour. I looked up details of his flight a few weeks ago and was horrified to discover, and it shattered my childhood recollection, that the flight lasted for 1 hour, in which time he did a complete circumnavigation of the Earth. But it took off at, I think it was 6 o'clock Greenwich Mean Time. So when I went out in the dark at about 8 o'clock at night, he was well landed, and my dad was telling me a fib. But yeah, I haven't forgiven him for a fortnight. Anyway, yeah. But it did spark my interest in astronomy, and I've always been interested then in small telescopes and images. So the brother phoned me up and he said, look, I need a bit of help with my mathematical program that I'm working on. How did they measure the angles of stars? How did they map the stars? And I thought, well, that's easy. You just use one of something a bit more sophisticated than that. And you sort of look down there, you line, I've just made this, by the way, it took me all of a minute because I lost the last one. You look up there, there's a star there, and then you read off, oops, sorry, I should have started there. Oh, where I put the scale in the wrong place. Oh no, I go that way. So I look up and I see, yes, there's a star up there, and I read that angle there and record it. Great, that sounds perfect. Of course, that's nonsense, because in the 5 minutes that it's taken to do that, we've gone round, and the star is in an arc in the sky, has gone down. So it's a different angle there than it is 10 minutes later when it's over there and it's gone down a bit. That is a bit of a puzzle. We'll go into that in a little bit more detail. But for 2000, what are we now, 2023? Yeah, so over 2,200 years ago, it can't be, one and a quarter thousand years ago. Is that right? Oh, what are we, 20? Yeah, it's 2,000 years ago, since BC almost. 2,200 years ago. The Greeks and the Egyptians were fascinated with the heavens. A chap called Aristarchus, actually, he was a real outlier. He said, I think that the Earth goes round the sun. And he was shut up. His mate Plato wasn't his mate for very long, and Ptolemy, round about the same time, said, no, Earth is the centre of everything. And old Aristotle came along and said, it must be. We're the centre of things. We're the chief. That's we must be in the centre because we're us. And they had the backing of divinity to support this. There are very abstruse biblical references which have been built on over centuries. One is in Joshua in the Old Testament. It refers to God commanding the sun and the moon to stop in their movement across the sky, so that whoever it was, the Israelites or somebody other could fight a battle to the close and win, in daylight. So that proved that the earth, that the sun moved because God had commanded them to stop, sort of. There's I think a couple of references in the Psalms. Psalm 91 or 93 suggests the earth is immovable, stationary, immovable. It says, it doesn't suggest, it says. And if you interpret it and want to interpret it in the way that that it was interpreted, then Holy Scripture says the earth does not move. And that held sway. Of course, the churches became stronger and more influential. Influential through a network of priests and clergymen, bishops and a pope at the top in general in the Western world. But the influence that they had on monarchies and the influence that they had on, universities, for example, armies, regulatory authorities, meant that there was no change in this sort of thinking for at least 1,500 years. Indeed, there were various inquisitions. There was a Spanish Inquisition, but I can't quite remember that. There was certainly an Italian Inquisition in the early 1600s. But along came an extraordinary man in Poland, a guy called Copernicus. That's his Latinized name. I think Copernicus or something like that. Copernicus is how he's known today. He was a polymath of extraordinary ability. He had the advantage of being able to afford, or his father enabled to afford for him, a university education. And he was a mathematician of significant repute. He was a churchman. He was a canon lawyer. He was an extraordinary man, but he had a fascination for the stars. And he had a sort of independent streak of mind. He must have done, because he was a professional within a creed, a doctrine that said the earth is the center of everything, God is supreme, his teachings, brackets, and our interpretation of them are that we are the center of the world. They even to this day strongly interpret in the beginning was the Word, and the Word was with God, and the Word was God, and the creation, and so on and so forth, and they interpret that as geocentric. The earth is the middle of everything. And supporting that, of course, what do you see? This is just nothing to do with divinity or anything like that. It's just what you see if you look up at night. I try and illustrate this with an umbrella. That was a shooting star, by the way. These were just set up as an example of what you would see on a dark, clear night. Not very common in Ireland, I have to say. I might say a bit more at the very end. And over here, there's supposed to be, there is a star there. So there's a star. So if you look up in the night sky and look north at about that angle, you would see a saucepan, which is a constellation called the Plough. High in the sky, it's not red, but I've marked it as red on there, is the pole star, and we'll talk a bit more about that in a sec. And then a big W, that one is the one that just flopped off, sorry about that. And if you watch it over 24 hours, the whole thing rotates around, and say, there's the horizon. Oh no, there's the horizon. These are so-called circumpolar stars. They never go below the horizon. So you would see in 24 hours, they rotate round 24 hours, 360 degrees. But because the Earth has moved round a little bit, round the sun, before they come back to the same spot, they've got to move on a little bit. That moving on a little bit happens every day. It's about a degree a day. So in 360 days, or 365 days, it's moved on. So roughly, that is what you see in the sky. Oh, there's another shooting star. Keep your eye open just as I'm on the subject, and this has nothing to do with this talk. The middle star in the Plough there, which is the saucepan, is an interesting one. It's a test of eyesight. If you look at that on a dark, clear night, you can pick it out quite easily. Up there, that's north. That that's actually a double star. Two stars which circulate around each other. They look very close. It looks like the moon and the Earth, except they're tiny dots of light. One's bright, one is very faint. It's just within the limits of good human eyesight. But they circle around each other very slowly. Extraordinarily, we're a long way from the moon, 240,000 miles, whatever that is in kilometers, something of that order. These things are so far away that the distance between those two stars that circle around each other is measured in light years. It's about half a light year. And bearing in mind that it takes from us to the sun 8 minutes for light to travel, this being half a light year, it's millions and million miles. It's extraordinary. And yet, you can hardly see that they're that far apart. To me, that is just one of the wonderful, and by the way, extraordinary and sort of vaguely sort of artistic sort of feelings that you might get with us. So, what am I saying? That's what you see if you look up in the sky and you're looking at stars. In the daytime, you see the sun setting over there, slightly southerly, and it comes up over the and sets over there in the west in 12 hours or 14 hours or 8 hours, depending on whether it's winter, summer, or spring, and it moves at slightly different heights, but it seems to go from there to there. Why wouldn't it be going around us? The moon, likewise, once a month. When you can see it every night, starts over there, moves round in the same direction. And the moon, interestingly, has different phases. A full moon. I love this. Andrea has just lent me this. Here's the moon, here's the sun. Can we turn the light off over there? Thank you. And we just indicate the phases of the moon. So just the first one. Oh yeah. So here's the sun, and when you see it from where I'm standing, and probably from where you're sitting, you see pretty much a full moon. But gradually, as the moon changes its position in the sky from where you're sitting, although I'm still seeing a full moon because I'm standing on the sun, and I'm not scorching, you'll notice that the moon is becoming, I'm not looking at the projection on the wall there, I'm looking at the actual illuminated section of the moon. So you'll see the phase of the moon there on the moon itself gradually getting smaller and smaller. I hope you can see that from here. And of course, when it gets around to there, sorry to shine that at you, there's an eclipse, so you can't see the sun. The moon moves across it. So I'm just going through the various things that you see. So moon, sun, stars. Planets are a difficulty. I don't know if you've looked up and seen planets. Planets are obvious. They are generally brighter. Venus, which we'll see a little picture of shortly, is a wonderful spectacle, a beautiful beacon in a sky. It's always an evening star or a morning star. You wouldn't see it beyond 9 o'clock at night at the very latest, I would think, before it disappears below the horizon. Or the sun is up and it disappears because the light is too. Venus, Mercury, similar, but you rarely see Mercury, certainly in Ireland. Mars, quite often seen. I'm not sure that it's really visible at the moment. Clearly very red. Jupiter, nice and bright. Fantastic view, which we'll say a little bit more about even in a pair of binoculars. Saturn, yellowish, less. And then Neptune, Uranus, forget about it, little dots. But they move differently to the stars. Whereas the stars move together as a body, the relative positions of the stars are constant. The planets move at a different rate, A to each other, and B to the stars behind them. And that's always been a bit of a problem for the geocentrists. But what they said to overcome that, Messrs. Plato and co., was that, well, of course, the stars must be embedded in glass spheres, which keeps them all in relative position, one with another, and moves them all round together. And the planets must be bedded in another glass sphere, but they move at different speeds. It still doesn't account for the fact that they move at different speeds relative to one another. And so that was a bit of a difficulty, but that was glossed over. God is great, mysteries happen. But that notion lasted for years and years. Copernicus came along and said, lads, that ain't right, that doesn't sound right to me. We can surely do better than that. And he studied old texts. He wasn't much of an observational astronomer, but he decided that what would happen that instead, in looking at the stars going overhead like that, or the moon or the sun, instead of them moving, could it be that I could be moving myself? And it's making it appear that these things up there are moving as well, are not moving at all. Interesting notion. And he came up with various other features of unexplained stellar or planetary motion. One of these is, I don't know if you've ever seen this, and it's slightly awkward to explain, but if you could measure the angle of planets and plot on a map of the constellations that you can see where the planet is actually moving relative to the background of stars, it's strange that Mars, for example, seems to be heading nicely, but it's moving backward against the background of stars. But then it goes through a big loop and then heads off again. How can that be? That has never been properly explained. Plato had a go and said, he said, well, there must be a little eccentric glass sphere for Mars, and that gives it its funny little wobble. But this is sounding more and more preposterous. On the other hand, God is great, divinity is right, the church is very strong. The Pope had something to say about this, and he said, lads, no, a whole string of them, and the Catholic tradition. No, the earth is the centre. This was in late 1500s when this idea came to Mr. Copernicus, and he was cautious because the church authorities were beginning to flex their muscles a bit and say, we must stop this sort of heresy, this nonsense. So in 1600, or just towards the end of the 16th century, 1598 or 9, a gentleman by the name of Giordano Bruno, nobody's ever heard of him, but he was a sort of free-thinking radical churchman who seemed to believe in a number of eccentric features that didn't quite go with the current divinity or understanding or appreciation. And the church hierarchy set up a Roman Inquisition in about 1600, and they summoned Mr. Bruno to come and account for himself. They did not like the fact that he said the earth moves. He said, I have this evidence to suggest the earth moves, and that comprises things like this strange orbiting of the plotting of the planets against the background. And the sloshing of tides, that's surely to do with something moving and the earth moving and the water slishing and sloshing around. The church did not like it at all. Poor old Bruno, 1600, was put to the torch. He was burned to death as a heretic. And Mr. Copernicus at the time, who was middle-aged, became very wary about how and what he published. Now, I think he did publish one or two documents, one in his own name, one in the that's great, in the name of his apprentice. I forget the chap's name now, but just to get the idea out there. And then along came my favourite astronomer of the 17th, 16th, 17th century, a man called Tycho Brahe. Tycho Brahe was a Dane. He was a nobleman, well got, bit boisterous, and his hobbies were carousing, fighting, and astronomy. Yeah, odd mix. But he was very, very particular when it came to his astronomy. And he had the money, and his dad was wealthy, and he was in the good books of the King of Denmark, who threw a few quid at him. And he developed and manufactured and measured the heavens with extraordinary accuracy. And he used an industrial version of one of these, pretty much. Instead of that diameter there being, 3 inches, the diameter on his huge quadrant device was about 6 feet. And the beauty of that was that he was able, it was mounted on a solid frame, on a rigid, a stable sort of central axis, and everything was slow and meticulous, and because of the length there, it was extremely accurate. You know, you can read that, well, that's about, let's say, 10 degrees, but actually, if you read it down there, it would be 9.317 degrees, because of the sort of magnified exactitude of the larger instrument. It was called a mural quadrant. It was sort of mounted with a chair here on a wall with a sighter tube, which was at the center of a quadrant, at the right angle of a quadrant, and the thing was raised. The man sat on his chair and looked up there and said, yeah, left a bit, right a bit, yeah, got it. And they measured very, very accurately. But they only measured at midnight. At midnight. Why is that? Just a quick little demonstration. Why would you only measure at midnight? And it's all to do with the fact that the Earth is continuously turning, as I'd already mentioned. At midnight, Earth, Sun, and the Earth is actually spinning. Now, Tycho Brahe didn't know this at the time, but he did know that at midnight the Earth was pointing in a direction directly away from the Sun. He did know that. That could be accounted for by his idea the Sun was actually rotating around the Earth in an orbit, or it could be accounted for the reality, which is the Earth is actually spinning itself. But knowing that direction and then measuring that elevation gave him an exact position of that solar object, stellar object, to the Sun and the Moon. Whereas if he did it at any other time, he'd be measuring it at an angle. Instead of measuring that angle there, he'd be measuring at that angle there, which is really not much use to man the beast, unless you try and take account of rotation of the Earth, which is awkward.
Geoffrey, I don't understand how the Earth is pointing away from the Sun. Is it the North Pole? Or?
Why is the Earth pointing away? At the point where you're taking the observation, the Earth appears. Now, you don't know if the Sun is going around it, but let's say at the moment, let's say there's the Sun. If he measures there and the Sun is here, he's not getting he has no idea really where an object might be, and the only place that he knows that the object might be is when it's midnight. He knows that the sun is directly behind him. So it's taking account of this angle as well. We might say a little bit more when we get onto that device there. So Tycho Brahe, he took hundreds, thousands of angular measurements of the heavens at the most creative, exceptionally detailed astronomical measurements. That's one thing, one of his great claims to fame. The other two great claims to fame, one is he recruited a young man called Kepler. Kepler, I'll say a little bit more about him in a sec. The other thing is he loved fighting. And what I love about this man is he had a dispute with his cousin over drinks, and a woman, I think, in the pub. And so they decided to have a sword fight. And his cousin chopped off his nose. Yeah. So I have a picture of him somewhere. Mr. How does this work? Here. So this is my favourite man, Tycho Brahe, and I'm sure that's a very flattering cosmetic nose. That's not what we're here to talk about, but it does amuse me that the poor fella had no snout of his own. Actually, they exhumed his remains. They've done it twice, because a major astronomical argument was what his nose was made of. So in the 50s, I believe, his body was exhumed because they weren't sure if it was gold or brass or copper. But the exhumation back then didn't have the technology that they have now. So in 2000, they exhumed his bones again just to check on his snout. They discovered the elements of brass, which are whatever they are, tin and copper, is it, or whatever it is, in his facial bone, the remains of his facial bones. So he had a brass snout. Now you see some pictures of him, paintings of him, with an enormous big sort of gold proboscis coming right across his face. But this one looks as though it's been heftily modified. Anyway, Tycho Brahe. He took loads and loads and gave them some ideas, but Tycho Brahe was always cautious of the church himself, and he didn't like to commit himself to the Copernicus's new thinking that actually the Earth travels round the sun, and the planets probably did the same. No, he just was not happy with that. But his apprentice. There was one other feature which is quite important. Why he did not accept that the sun didn't travel around the Earth, and that was that if the Earth travelled, not only when you threw the ball up in the air, it would land over there because you were moving away from wherever it was travelling, and which time down it comes. And we know that doesn't happen. But the other thing is, if it was moving and you were looking at the stars over there, when you moved over there, suddenly the stars would shift. There would be, and they're not all at exactly the same distance, despite what these people with glass domes said. There's some glass domes, beyond other glass. I don't know. I can't remember the exact details. But there would be what's called a parallax effect. So if I'm standing here and looking at that newspaper on the table there, when I'm here, it's over there. But when I'm here, it's over there. It's not at the same angle. That phenomenon there of changing angles because of movement is called parallax. So if the Earth was moving, then the stars would demonstrate some parallax effect, and they would get out of shape and out of order. So as they don't do that, then we're clearly the Earth can't be moving, and therefore divinity, the church and all that old stuff must be right. So the throwing the ball, the stellar parallax effect. But the further away, just to put that into some sort of context, the further away the star, the further away the object, so if I stood over here and moved the same distance, actually the angular displacement that I would see is much smaller. And further and further and further away, that angular displacement almost becomes nil. So that, just by way of example, sorry, cricket is my other interest, sorry, John. If that is the Earth, this dimension of whatever it is, a couple of inches, the moon, where's my little yellow ball? There would be about 1,000 times that, whatever that is, about 5 meters away. So about over by the door would be the position of the moon. The sun would be at the gates of the new GAA, down on the Yall Road, about 750 yards away. That would be the sun in comparative sizes. And the nearest star would be, anybody got any idea, any guess?
4.5 light years.
It's 4.5 light years in equivalent distances. Earth, moon, GAA is the sun. The nearest star would be about halfway to the moon. That would be the nearest star. So stellar parallax, even if it were to happen, over the distances that the Earth actually, we know now, does move, is completely undetectable. You're talking of 10 to the 12th, 10 to the 11th kilometers or something like that. That's 10 with, that's 1 with 11 zeros after it. So 100,000 million, whatever it is, miles. I worked it out last night. It took me about 40 minutes on the train. So what we know now, the actual dimensions are huge. Anyway, that was Mr. Brahe did lots of good basic work on measurements, but then failed to interpret. Kepler came along, his apprentice. Fortunately, Tycho Brahe, fortunately for Kepler, he snuffed it, and Kepler said, "Could I have the readings?" He spent years, again, worried about what the church might say about him. But he analysed the readings. He thought, how can this be? Moving on, just to give a little bit of an explanation, if I can. He plotted, he drew a diagram. If the sun is the centre, and if the Earth moves round the sun, some sort of circular orbit, and if we have managed somehow or other to measure these angles over several years, let's say we've been measuring the angles of Mars, and let us say we think that Mars moves around the sun as well. When the Earth is in this position here, position 1, we know because we know the date, so we know its relative position to the sun, and we measure that Mars is in this direction somewhere. We don't know how far, and we just call this, we don't know how far we are from the sun, but we just call this a distance, let's call it d, from the Earth to the sun. We've measured that angle. Some while later, we measure another angle. Maybe years later, Mars comes back to the same position, and we measure another angle, and we know it's in that direction. Then we have two positions where they interact. There's only one point. So Mars must be located there. We know how many days it's taken to get from this point to this point. So if it's taken 182.5 days, that's half a year. In fact, we haven't, let's say it's a quarter of a year. That would be roughly 90 days. We know that each 90 days, in 90 days, a quarter of a year, we go a quarter of the way around our orbit. So we know that. We know that our orbit is D. Don't know the exact what D is, but we can draw a scale diagram and therefore measure the distance from relatively straightforward scaled mathematics. We know that length, we know that angle, we know that length. We can scale that length there. And one of Kepler's great discoveries is being able to say the ratio of distance between planets can be established. And the technique that he used was measuring angles. Absolutely fundamental. Exactly the question that the brother asked me, and I said, "What the hell do we do that?" Now, it's not quite as easy as that. The other thing that this wonderful man, Mr. Kepler, did was he asserted that the planets didn't go round in circular orbits. Circles are perfect, it's what God would ordain, they were the perfect figure. But actually, no, they don't. They're slightly squashed. They're sort of slightly egg-shaped, elliptical, actually. And Kepler asserted that planets actually go round the sun in elliptical, egg-shaped orbits. That became his first law. Actually, it's called Kepler's first law, planets go round the sun. How did he come to that conclusion? I found it. I went home and made another one of those. There we are, that's the same sort of thing as that. So I don't know if any of you made pinhole cameras when you were school kids, but pinhole camera, or have been to a thing called a camera obscura. Basically, this is a shoebox, and I've put a little screen at the back, and if I point that at the light or at the sun, a small image of it appears on here. Now, you need to look into it, and I'll leave it on the table. But it will show a small image. So if you point this at the sun, and you put a scale on where the image appears, you can see that the sun is sometimes that big, and sometimes it's a fraction bigger, and sometimes a fraction smaller. So you can actually measure the diameter of the sun on different days in the year. Sometimes it's fat, sometimes it's thinner. But when you come back, it might start off there and it's nice, big, broad diameter. When you get to there, it's small diameter. When you come back there, it's still small and it's getting bigger and bigger, and then it's back to medium size again, and then you're back. And that's exactly what you find if the orbit of the Earth is elliptical. That gave him the idea. So two things, elliptical and measuring the relative differences. He was, and all this was adding to the idea that we revolve around the sun, the key thing. He again was very, very nervous. He'd seen what had happened to his man Bruno, who was burned at the stake. He got his own sidekick to publish papers on his behalf. But actually, he established 3 laws from his observation. And it's just so wonderful how he used and developed the mathematics of orbits from cold observation, cold experimentation, reviewed his results, put aside any notions of human assumption, grandiosity, divine intervention, religious interpretation, and just used the numbers in front of him. And this process was the foundation, of modern astronomy, but as important, or more important even, was a change in the way of thinking, which led eventually to the so-called Enlightenment at the end of the 17th century, when people like Isaac Newton and so on came along. And the scientific method seems straightforward and obvious now, that thought processes work in the world of mathematics, science, astronomy, technology, by somebody having an idea, a theory of how it could work, then setting up an experiment or making observations in a specific and specified manner, making sure that it's repeatable and it can be reviewed by other people working in the field, assessing the results analytically and dispassionately without, and it's difficult, the overriding of human preconceptions and assumptions, publishing results and opening them to public scrutiny. That process is called the scientific method, and it is fundamental to all the thinking that came subsequent with the great scientists, and particularly Isaac Newton, who developed Kepler's work and Kepler's theories. And that is the transformation, really, that came about from being driven by human preconception, human hubris and arrogance, over-interpretation of divinity. And by the way, I'm certainly not saying there is no God. It's just how he has been interpreted. And some of the spurious ideas, like throwing the ball up in the air, we can't be moving because it doesn't come down over there. And I find that whole process creative, wonderfully imaginative, tremendously difficult when you just work out the detailed particularities. And of course, by the way, in all of this, I've forgotten to mention Galileo. Must give Galileo a plug. Great man, another nervous scientist. One of his great contributions in supporting the work of Tycho Brahe around about the same time was he didn't invent the telescope like most people say. That was invented, I think, in Holland sometime by a spectacle maker. But lenses were freely available and were beautifully manufactured. I have a couple of lenses that I dug out at home. It's not round, but a simple telescope is made by magnifying glass, another magnifying glass, and putting one up against the other. And that, I would estimate, I'm magnifying that bookcase over the far side about 1¼ times. It's actually the ratio of focal lengths, but we won't bother going there. And it's upside down. So one of his interesting developments, and I went along, plug for Wiley McGrath here, Wiley McGrath the other day, and I said, what I need is a concave lens. Instead of a magnifying lens, a concave lens has faces that are like caves. They This one is, no, this one is plain that side, concave there. But when you use that as the lens, I'm looking at the gentleman with the camera at the back there now. Oh, gosh, he's handsome. Yeah, I magnified him twice. But Galileo used this type of arrangement and do help yourself make your own telescope afterwards and just see. But one of the things that he discovered which influenced him was the moons of Jupiter, using a telescope that magnified only, some people say 4, some people say 8 times, some people say 30 times. I know it works with 8 times, I'll say why in a sec. And he discovered the moons of Jupiter. And over a period of a week or two, he could see Jupiter there, and the 4 little moons, four of the 13 little moons, and they moved in relative positions. And he thought, actually, how can that be happening? At first he thought they were stars that just happened to be roughly in line with Jupiter, but they were moving and they disappeared. One of them disappeared behind the main planet. And then you realise they're circling around, circling. Orbits do happen in space. He was another one who saw the sloshing of tides and thought that must mean that we're moving somehow and sloshing our tides around. That's a whole lecture in itself, a wonderful lecture. How do tides work? Why are there 2 tides a day? Not a lot of people know that. That's another day's camel ride. So he said, Jupiter. He looked at Venus through his telescope, and the first time ever, although it is said that you can see the phases of Venus with the naked eye, there he could see quite clearly the phases, like the phases of the moon, he could see the phases of Venus. Now that is great. I won't go into huge detail, but if it's a geocentric orbit, and Venus is going round the Earth, and the moon is going round the Earth, you would only see half the phases. You'd either see the crescent shape or you'd see the greater than half. You would not see them both. And he saw that through the telescope he could see at different times different phases. That says Venus is going round the sun. We'll talk about that in detail later if anybody's more interested. But that was another of the pointers. But poor old Galileo, though he tried publishing some info, fell foul of these nasty fellows up in Rome, and was summoned before the Inquisition in about 1635 or thereabouts, was found guilty of heresy himself, and he was subject to house arrest, mercifully, not like Bruno 30 years earlier was he put to the flame, but he kept his gob shut for the last 8 years of his life, and who wouldn't? So Messrs. Brahe, Galileo, started by Copernicus, finished by Kepler, led to this transformation, and over 100 years, the whole change of mindset of people, that cannot be right. Oh, it possibly could be right. We'll make sure we force those bastards to agree with the traditional view. And gradually things changed. Until 1635, 40 odd, after the death of Kepler, people realised that we're onto something here. That is the transformation. That is a wonderful, wonderful transformation. Just by way of a little finishing up example, what does it feel like to something that is so counterintuitive, something that it's so hard to believe, but in fact is actually true? And I like 2 examples. The boys hurling team wins a great final, and they're going to have a presentation at the pitch at the halfway line next week's match. So the chairman, John, comes along and he says to the groundsman, you know that rope that runs from that corner to that corner, marking the sideline? He said, what I want to do is lift that rope up in the middle so the team can come marching on like this. We put bunting along the rope, and the boys can march underneath the central circle, and we can have the ceremony and so on. So there's an idea. So here is the football pitch, and there's one end, and there's the hurling pitch, or whatever. Let's call it football, because that's what I was thinking of originally. It's only because my pal happens to be there. Anyway, so they've got this rope that runs along the ground. They want to lift it up in the middle, and now the lads are 5 foot tall, so they want a bit of bunting on the top. So leave it clear of the lads, anchored at each end, but of course it's not going to reach because it's got to go that bit further, there and there. So you need an extra piece of rope. Now, let's say there's no sag. The question is, how much extra rope do you need? And it's one of these answers. it's either, bearing in mind that this is 100 yards between there and there, it's either 7 inches, 7 yards, or 17 yards and 7 inches. And the question is, what is the extra length of rope that you think you'd need? And this is totally counterintuitive, I think, from most times I've asked this question. Bearing in mind that we want to lift that up so that it's about 6 or 7 feet up, let's say 7 feet up. How much extra rope? And the answer, surprisingly, is that. That seems so counterintuitive. Hey, 7 inches to lift it that much. That's one little question. I just think that, this is hinting at counterintuitivity. That's nothing in comparison with a complete mindset, but this is a bit more difficult. The sum, if you add 1 plus 2 plus 3 plus ... and keep going forever, what does that sum to? This seems so counterintuitive. And the answer could be, let's say, something ridiculous, minus a 12th. The answer could be infinity. Or the answer could be some incomprehensible number, which is infinity to the power infinity to the 6th. That's infinity to the infinity to the infinity. But this number goes on infinitely. It's getting larger and larger all the time, adding itself. The question is, what is that? Demonstrable, and I will do it later if you want me to prove it, but the maths is slightly awkward, and I'll probably refer to YouTube. The answer is actually minus a 12th. That is so extraordinary. How can that be? And why I'm saying this is it just gives an indication of how strange it must have been for accepted, received wisdom to be completely turned over on its head. That seems almost impossible, but is actually a technical equation that's used in nuclear physics, and demonstrable. It works and is fairly straightforwardly proven. So I've said more than I should have said, and probably whatever. Thank you very much for coming. And there are bits and pieces of stuff over there that you're welcome to have a look at. Do treat them with caution. A few things I haven't mentioned. Device that I made for measuring angles, solar angles and stellar angles, and bits and pieces of pinhole camera and so on. Some tops there, which I forgot to mention. One of the motions of the Earth, which was predicted, was precession, but we won't go there. That's for another day. Thank you very much for being my audience. Thank you. There you are. Don't forget Tycho Brahe. The tides will be very interesting. The tides, I just love it. Why are there 2 tides a day? Oh, I was going to talk about precession, and just because one of my little sidelines is tops. I have quite a nice collection of tops, and this is one that I'd never got round to opening. Oops. And this was to demonstrate the 3 types of motion of the Earth. So there's the Earth, and it sort of spins round. It goes round the sun, as we now know, and it's spinning on its own axis. But what I'm trying to show as well, the 3rd motion that the Earth has, is called precession. And precession is when it starts to slowly wobble in the axis. Well, the axis itself starts. It generally begins to as though it was drunk, and that is actually happening to the Earth, and that is why the pole star, which currently is directly above the axis, is currently above the centre of rotation will, at some future time, move away by several degrees as the Earth wobbles.
Gradually, you mean?
It's gradually beginning to wobble. Well, it does wobble now, actually. It is in the process of wobbling. So in 1,000 years' time, the pole star will not be in the centre of rotation of the axis of the Earth. There it is, wobbling, wobbling, wobbling. Oh, I get them all over the place. I've got loads of these. This is a particularly fantastic one. It's this is one of my favourites. It's nothing to do with this, but just a lovely little thing. Ooh, I need a flat table.
Yeah.
But the old snake goes, nothing to do with astronomy. Right, you get the general idea.
Yeah. It's always like
But so no, that was just precession.
Geoffrey, is it true that when we're closest to the sun, that's winter?
Yes, it is actually.
Yeah.
It is.
It's just that we're turned at the wrong angle.
Yeah, we're turned at a different. Yeah, that's right. We're closest, but and this is what I use for pursuing my interest in astronomy. I wanted to clamp. I had this old tripod. I wanted to clamp my binoculars because you can't hold binoculars still enough. So I made I just found a piece of plywood and I put a little screw nut in the bottom, and I just mended a puncture on the bike actually. So I found a little piece of inner tube, and so it works quite well. I found a bog handle, and I found a toilet roll holder for the handle. Yeah, almost unused.
it's very professional.
But the reason it's as such it's not professional is that there's a bit of slippage there. So what I thought this was my minor masterstroke. I can pump it up, yeah, and that's got it nice and handy now. So that's not going to go anywhere. And that's perfectly good for viewing Jupiter. It's wonderful. And you can see the moons, you can watch them, over a couple of days, a few days, moving around. And you can even see the stripes on Jupiter if you've got good eyesight, which mercifully I'm reasonably blessed with. But yeah, that's the Eastway clamp. There we are. That's it. No more. It's lovely to see you. Thank you for coming. Great to see you. Thank you very much.